Hey guys, Mrs. Traver here. We're going to do a section 4-6, solving exponential equations. First time we're going to look at is equations with common bases. So in this first one, number one, we've got 3 to the x equals 3 to the 2x minus 5. Notice we have 3 to the on both sides. And normally when we get rid of 3 to the, if we try to get rid of an exponent, we do the log of that base on both sides. And so if we did that, then we'd have log base 3 of 3x equals log base 3 of 3 to the 2x minus 5. And then those logs would cancel. So what I'm getting to is there's this thing that you might notice is that if we have a common base, if we log both sides, those would just go away. So I'm going to end up having the exponent equals the exponent. So you can skip this step here and just recognize as soon as you have a common base that you have the exponent x equals the other exponent 2x minus 5. That only works when you have the common base and that's the only thing on each side. In this case, it did. So let's solve for x like normal from here. So take away 2x from both sides. And you've got negative x equals negative 5. Therefore, x equals 5. Now, we do have to check for extraneous solutions on these guys. And if we do that, we can plug it into what we originally had. So 3 to the 5th equals 3 to the 2 times 5 minus 5. When we check, we've got 3 to the 5th equals 3 to the 10 minus 5, which is 3 to the 5th equals 3 to the 5th. So that checks out, and x equals 5 is truly our answer. Now, sometimes it doesn't work out nice, so we do have to check for those extraneous. This time, that'll happen to be the case. So on number 2, say we had 5 to the negative 3a equals 5 to the 1 minus 3a. So let's see, we have a common base, so we can skip that logarithm step and essentially just get rid of those 5s. So then we had negative 3a equals negative 1 minus 3a. Solving for a, we could add 3a to both sides. On our left, everything is gone and we have 0. And on our right, we have 1, which is clearly not true. So we have no solution. In this case, we realized there was no solution while solving for a. Sometimes we solve for a, and then when we plug it in, there's no, the check doesn't work. So there's 2 types of times you'll get a no solution. Let's do another one. This time, they're not going to be common bases, but we're going to force them to be. So say we had, let me get a good example here. All right, let's do this one then. We've got 6 to the 4x equals 36 to the x plus 6. So let's check this one out. Notice this one does not have common bases, like I said, but you might be able to notice that there's something in common with 6 and 36. 36 is 6 squared. So I'm going to rewrite this as 6 squared. And then this x plus 6 will just kind of tag along here as part of the exponent as well that I'll have to multiply in. So on my left now, I've got 6 to the 4x. On my right, I have 6 to the 2x plus 12. Now I've got common bases. The exponents are simplified. I can get rid of those 6 to those on both sides and just solve for the equation 4x equals 2x plus 12. Now get all your x's to the same side. And you've got 2x equals 12, so x equals 6. This looks good. Let's do our check. So if I plug it into the original, I have 6 to the 4x equals 36 to the x plus 6. So to the 6 plus 6. So on the left, I've got 6 to the 24th. On the right, I've got 36 to the 12th. Keeping in mind that 36 is 6 squared, we could rewrite like this, which we see these actually are equal. So the check worked out, and this is the solution. All right, let's try one more like this before we move on. How about 4 cubed equals 1 over 16 to the negative 2x. So again, we want to force these to have a common base, and we can rewrite 16 as 4 to the negative second. And then we'll multiply by that negative 2x on the top. So we can get rid of those common bases since they're the same now. We've got 3 equals 4x. Dividing by 4x equals 3/4. All right, we can check then. So if I plug that back in, I'd have, does 4 cubed equal 1 over 16 to the negative 2 times 3/4. So negative 2 times 3/4 is negative 6 over 4. So that's negative 2/3. And negatives flip the inside. So I'm going to keep messing with this right side. I'm going to make this be a 16 now and make it be a positive 2/3. Okay. 16 to the 1/3. Does anything times itself 3 times equal 16? Nothing nice does. So at this point, we can say that these are not equal. You could check it with your calculator as well. So this is not a solution. It is called extraneous. So we can say there is no solution. All right, I lied. Let's do one more of those because I forgot a different type of them. Say we had 9 to the 2p equals 27 to the 3p minus 1. So I want a common base, and you might be trying to find the base to be 9. Notice all the other ones, one of the bases was set up perfectly and the other wasn't. But we have to figure out what is a common power. What can we power up to get a 9 or a 27? And once you think of it that way, you'll realize that this is 3 squared and this is 3 cubed. So if I rewrite 9 as 3 squared and then I multiply by that exponent that there was already, and then I multiply again by that exponent, then we are all set there. So we've got 2 times 2p on one side, 2 times 2p on one side, and 3 times the quantity, 3p minus 1 on the other. So 4p equals 9p minus 3. So I've got 5p equals negative 3. So p equals negative 3/5. We can check it again. Let me pause so I can check. All right, so I left the check up to us to plug in and check. That one's a little messy with the fraction, so I just wanted to give you an example like that. But that one probably wouldn't show up on an assessment. Okay, so let's see what's next. We've done a bunch of them where we did equations with common bases. And now I want to do some where we don't have common bases. We actually only have one exponent at all. So for these ones, we are going to have to use logarithmic properties to solve. So for number one on these type, say we had like 10 to the x equals 18. And I want to get x by itself. So to undo that 10 to the, we have to do common log, because that's base 10, of both sides. So I've got common log of 10 to the x equals common log of 18. And then I did that so that this 10 to the would cancel out. And now I've got x equals log 18. Now, I want to get an actual answer for these. So on our calculator, there is a log button. You might not have known it was there all along, but it's right here. It's on any scientific calculator. Notice there's common log and natural log. So I can go common log of 18 is approximately 1.255. And that's about it. I'm not going to ask you to do checks of these ones. Number 2, let's do 2 to the x equals 7. So to get rid of that 2 to the, we want to go log 2 of both sides. That way, on the left, we've got log base 2 of 2 to the x. And on the right, we have log base 2 of 7. Now on the left, we did this log base 2, so those would cancel, and I'd be left with just an x on the left. On the right, I have log base 2 of 7, and here's where we maybe run into an issue, because on our calculator, as I just pointed out, there's log, common log, and there's natural log. There's no log base 2. So this is where we need a new formula, or maybe not one new to you, but or mind your own formula, which is called change of base. So here's how change of base goes. If we have the logarithm with some base, b, and we want to change it to either common log or natural log, because that's what's on our calculator, that's what we're going to use. Let's choose to do common log. So I can change this to being common log of a over common log of b. And this is just a rule here that we'll use in this problem. So notice it's a over b, its base goes bottom, however you want to think of it. So if I have log base 2 of 7, this is equal to common log of 7 over common log of 2. And now that I can type in my calculator. This I cannot. So typing this one in, just simply jump in and say log of 7, enter, divided by log of 2, enter. So we've got approximately 2.807. Be careful. If you try to type it in all at once, just words of the wise, if you're going to type it in like this, then be careful that you close out your parentheses here at the end of this log and here at the end of this log. Notice if I don't close my parentheses and I just start doing my divide by log 2, you get a totally different answer. So you have to be careful because here it was trying to do log of 7 divided by log 2, not log of 7 divided by log of 2. So we want the top answer, 2.807. So this is approximately 2.807. All right, let's do another one. How about 7 to the 9x equals 15? So you might be noticing the trend here. We're going to do log base 7 both sides. When I do my log base 7 to this side, the 7 will go away. It'll just be 9x. And over here, I need log base 7 of 15. Now, I still need to divide by 9, but I'm going to mess with this guy first. I'm going to write it as log base 15 over log base 7. And I'm going to simplify this piece out before I divide by 9. So log 15 over log 7 is approximately 1.392. So now I've got 9x is approximately 1.392, and I can divide 9 from both sides. And if you left your value sitting in the calculator and you didn't clear it out, then you can just say divide, and it'll know that you mean, hey, take my last answer and divide it by 9. I get 0.155. X is approximately equal to 0.155. And also notice we haven't been doing our check of these, but if you wanted to, you could. If I checked this, I would have done 7 to the 9 times approximately 0.155. And when I hit equals, I should get something close to 15. I say close because we were doing approximations the whole time. And there we are. We got something pretty darn close to 15. So you can say that checks out. It's hard to say it's it's hard to write a check without having an exact answer, though. If I had truly plugged in log 15 over 9 log 7 into that x, then it would truly work out to be exactly 15. But that's a lot of plugging in, so I'll say skip it. All right, next one. Let's do some with some more steps. Oops, we're on number 4. So number 4, let's do 7 times 4 to the 7m equals 67. So first things first, I've got this 7 on the outside. I need to get that out of the way, so my exponent's by itself first. So divide both sides by 7 first. And we're going to get a decimal right off the bat. 67 divided by 7 is about 9.57. I've been using 3 decimals. Let's do 9.571. And now I can do my log base 4 on both sides. When I do it to the left, the 4 will go away, and I'll be left with just 7m. Over here, I'll have log base 7 of 9.571. So I'm going to rewrite that as change base. Common log of 9.571 over common log 7, which is approximately, let's see, common log 9.571 divided by common log 7 is about 1.161. And then lastly, divide out my 7. And I have 0.166. So there is our answer. All right, I am going to leave it there. We did 4 of them using logs to solve. We did several of them where we were trying to get a common base. I will see you guys next time.